All right, let's dive in. Today, we're going deep on large time series models, or LTSMs for short. You know all those large language models you keep hearing about in the news? Well, LTSMs are kind of like their time-traveling cousins. They're all about finding patterns in data that changes over time.
Yeah, it's a fascinating area. Time series data is everywhere, but analyzing it effectively, really understanding it and making predictions, it's always been a challenge. That's where LTSMs come in. They have this huge potential to change how we understand all sorts of things that happen over time in just about any field.
Exactly. And for this deep dive, our main guide is a paper called Timer. Generative pre-trained transformers are large time series models. Think of it as our map for this episode, showing of the ins and outs of these powerful new models.
And one of the really interesting things is we're already swimming in time series data, as you mentioned. So why do we even need these large models, right? Well, the paper uses a really good example. They point out that even some of the most advanced models out there, like PatchTST, which came out just a couple years ago, struggle when they only have a small amount of data to train on.
Ah, so it's not just about having a ton of data, it's about the quality too.
Exactly. It's not just about quantity, it's about quality. The paper digs into this idea of high quality data. The researchers specifically looked for data that had repeating patterns, behavior that was consistent over time, and a degree of predictability. Basically, data that was rich in information and reliable for analysis. They identified three key characteristics: periodicity, stationality, and predictability.
Okay, so break those down for me. What do those actually mean in plain English?
Sure. So think of periodicity like cycles, like the regular rise and fall of temperatures throughout the year. Stationality, on the other hand, means the data behaves pretty consistently over time, like a steady heartbeat.
Okay, I'm with you so far.
And then predictability, well, that's just about how well we can actually guess future values based on past data.
Got it. So they're not just grabbing any old time series data, they're being really selective about what they use to train these models.
Precisely. And to get that high quality data, they actually created their own massive collection called the Unified Time Series Dataset, or UTSD. It's a huge collection of time series data spanning 7 different areas, from energy consumption to website traffic patterns. It's huge. We're talking up to a billion data points.
Whoa, a billion data points. That's mind-boggling. But with so much data coming from all these different sources, it must be really tricky to work with. How do you even begin to make sense of it all?
That's a great point, and it's one of the key innovations the paper addresses. Imagine trying to analyze a symphony with like dozens of instruments all playing at once. It's overwhelming. So they came up with this clever solution called the single series sequence format, or S3. It's like taking that complex symphony and turning it into a single streamlined melody that still has all the essential information.
So instead of treating each data source as a separate instrument, they're finding a way to blend them all together into one cohesive piece.
Exactly. And having this unified representation is really crucial for training a model that can work well with new, unseen data. By learning from this like universal melody of time series data, the model can adapt to all sorts of new and unexpected data sets much more easily.
Okay, I get it. That makes a lot of sense. So we've got our high quality data, all prepped and formatted. Now what? How do we actually build an LPSM that can learn from this really complex information?
Well, this is where the timer model comes in. At its core, it's a transformer model, which you might recognize from natural language processing. They've been incredibly successful there. But there's a twist here. They use a decoder-only architecture, which is similar to, the GPT models you've probably heard of.
Decoder only. Remind me what that means again?
Sure. Imagine you're writing a story. You don't need to like summarize the entire plot before you start writing the next sentence, right? You just need to remember what you've already written to keep the story flowing naturally. That's kind of similar to how a decoder only model works. It focuses on the flow of information within the data, predicting the next data point based on everything it's seen so far.
Ah, okay. So instead of trying to analyze the entire data sequence up front, it's more like reading a sentence word by word, building up an understanding as it goes along.
Exactly. And this approach turns out to be incredibly effective for time series data. The researchers actually tested different model architectures, things like MLPs, CNNs, and RNNs, but the decoder only transformer, it just performed the best.
So it's not just about having a huge model, it's about choosing the right architecture for the job.
Yeah, exactly. And the fact that they chose a decoder only transformer, similar to those GPT models in language processing, it really highlights how techniques from one area AI can be used to make breakthroughs in another seemingly unrelated area.
That's pretty cool. So this timer model, it's like a time-traveling storyteller, putting together a narrative from all the data it's given. But what kind of stories can it tell? What tasks can it actually do?
That's where things get really interesting because Timer uses this idea of generative pre-training. It can be adapted to a whole bunch of tasks, not just one specific job like forecasting.
Hold on, generative pre-training. What does that mean exactly?
Think of it like giving the model a really broad education before sending it out into the world. Instead of training it for one specific task from the beginning, we feed it a massive amount of data and just let it learn general patterns and relationships within that data. Then, when we do have a specific task in mind, we can fine-tune the model on a smaller, more focused data set. And it can use all that knowledge it already has to get better results.
So it's like teaching someone all the fundamentals of music theory before they pick a specific instrument. They can then apply all that basic knowledge to their chosen instrument and become a much better musician overall.
Exactly. That's a great analogy. And with Timer, this generative pre-training allows it to excel at three key tasks: forecasting, imputation, and anomaly detection.
Okay, let's break those down one by one. First up, forecasting. I'm guessing that just means predicting future values based on past data, right?
Yeah, that's it. And Timer does remarkably well, especially when it doesn't have a whole lot of data to work with. The researchers tested it on a variety of real-world data sets, things like energy consumption, traffic patterns, and weather data.
So, some pretty challenging stuff. How did it do?
It consistently outperformed some of the best models out there, even when it was only given a small amount of data to learn from. They even compared it to models that had the advantage of training on the full data set. And in a lot of cases, Timer still did better.
Wow, that's impressive. It's like giving someone just a few puzzle pieces and having them figure out the whole picture.
And that ability to do well with limited data, it comes directly from that generative pre-training we talked about. It's like Timer has developed this deep understanding of the basic principles behind these time series, and that allows it to make good predictions even if it hasn't seen a lot of the specific data before.
So it's not just memorizing patterns, it's actually learning the rules of the game.
Exactly. That's what makes Timer so powerful and so adaptable.
Okay, forecasting check. What about imputation? What's that all about?
Imputation is like being a data detective, filling in those missing pieces of a puzzle. Sometimes we have gaps in our time series data for all sorts of reasons, like sensor failures, corrupt data, or maybe just missing records. Imputation is all about intelligently filling in those gaps, making the data complete again.
Ah, so it's not just about predicting the future, it's about reconstructing the past, too.
Exactly. And they tested Timer on a particularly tricky type of imputation called segment level imputation. This is where entire chunks of data are missing, like having whole paragraphs missing from a text.
That sounds really tough. How did Timer do?
It did great. They used 11 different data sets and removed different amounts of data from each one to see how well Timer could reconstruct it. And the results are really impressive. It consistently beat the previous best model, especially when those larger chunks of data were missing.
So Timer can predict the future and piece together the past with pretty amazing accuracy. That's incredible.
Yes. And being able to fill in missing data like that, it's super important for all sorts of real-world applications. Think healthcare, finance, environmental monitoring, and so much more.
Okay, two down, one to go. What about anomaly detection? What's that all about?
Imagine you're monitoring, say, a patient's heart rate. Suddenly, you see a spike or a dip in the signal that just doesn't look right. That could be a sign of a problem, an anomaly that needs attention. Anomaly detection is about automatically finding those unusual events within a time series.
It's like having a really vigilant guard dog, constantly watching out for anything out of the ordinary.
Precisely. And Timer has a really clever approach to anomaly detection. Instead of trying to reconstruct the whole time series and then finding any deviations, it directly predicts the next part of the series and compares that prediction to what actually happens. If there's a big mismatch, that signals a potential anomaly.
Oh, I see. So it's like having a security system that not only records events, but also anticipates what should happen next. And if something unexpected happens, it sets off an alarm.
Exactly. And this predictive approach has some real advantages over more traditional methods. It's faster, it's more robust to noise in the data, and it can detect anomalies in real time as they happen.
Okay, wow. We've covered a lot of ground here. Timer can forecast, impute, and detect anomalies, all while handling limited data remarkably well. It seems like there's no stopping this time-traveling AI. But are there any limitations? What are the researchers still working on?
Well, as with any cutting edge technology, there's always room to make things better. One area the researchers point to is scalability.
Scalability, you mean making it handle even bigger data sets and more complex tasks?
Yeah, exactly. They've showed that Timer gets better as you increase the size of the model, which is encouraging. But training these really large models, it takes a lot of computing power and resources. So finding ways to make them more efficient and scalable is a big area of research right now.
So it's kind of like building a rocket. We know it can fly, but now we need to figure out how to make it even more powerful and fuel efficient.
I like that analogy. And another area of research is something called zero-shot forecasting.
Zero-shot forecasting? What's that?
Imagine being able to predict what's going to happen with a time series without knowing anything about that specific data beforehand. It's like being able to forecast the weather in a completely new city without ever having seen any local weather patterns.
That sounds almost like magic. Is that even possible?
It's still early days, but Timer has shown some promising results. And if we could do this, if we could generalize to completely new data sets, it would open up a whole new world of possibilities for time series analysis.
It'd be like giving a detective a brand new case in a city they've never been to and having them solve it flawlessly, just based on their general knowledge of how people behave and how crimes usually happen. Incredible.
Exactly. And while zero-shot forecasting is still on the cutting edge of research, Timer's early success hints at the massive potential of these large time series models.
All right, before we jump into part two, where we'll dig even deeper into Timer's performance and compare it to other new LTSMs, let's recap what we've learned so far.
We started by talking about the importance of using really good quality data for time series analysis, and we discussed how the researchers were very careful in how they built the UTSD and how they used that clever S3 format to combine data from all these different sources.
Then we looked at what's under the hood of Timer, and we learned about how its unique decoder-only transformer architecture, the one inspired by language models like GPT, helps it learn from data in this interesting way, like a time-traveling storyteller, piecing together a narrative from all the patterns it sees.
And we saw how that approach leads to really impressive performance on those three key tasks: forecasting, imputation, and anomaly detection. Even when the amount of data is limited, Timer does remarkably well.
It's clear that Timer represents a big step forward in the world of time series analysis. It's opening up new and exciting possibilities for understanding and predicting the world around us. But of course, the journey doesn't end here.
Come back for part two, where we'll talk about how scalable Timer is, how it stacks up against other leading ATSMs, and what this groundbreaking research means for the future.
It's going to be a fascinating ride.
Welcome back to your deep dive. As we continue to explore Timer, one of the questions that comes to mind is how does it handle really, really big data sets? Can it scale up to meet the demands of all those complex time series problems out there in the real world?
Yeah, that's a great question. It's one thing to have a model that works well in, a controlled environment, but it's quite another to actually use it in real world situations where the data is often messy and massive and just keeps growing.
You're absolutely right. And the researchers who developed Timer, they were definitely thinking about this issue of scalability when they designed the model. They wanted to make sure that it could handle increasingly large data sets and complex tasks without, any hiccups.
Okay, so how did they actually test timer scalability? Did they just keep throwing more data at it and see it happened?
Well, it's a little more sophisticated than that. They designed some experiments to see how Timer's performance changes when you tweak two things: the size of the model itself, think of it like the model's brain power, and the size of the data set it learns from during that pre-training phase.
Got it. So they wanted to see how much bigger and smarter they could make timer without sacrificing its performance. What do they find?
First, they looked at what happens when you just increase the size of the model, specifically by adding more layers to that transformer architecture. And as you might expect, a larger timer generally performs better. They saw fewer errors in forecasting as they added more layers. Essentially, you're giving the model more capacity to process information and learn those complex patterns.
So it's like giving someone a bigger, more powerful brain. They can handle more complex thoughts and ideas, right?
Precisely. And they found that this trend continued even when they really increased the model size significantly. They observed that the performance kept getting better with more layers and larger dimensions, which suggests that Timer has the potential to scale up even further in the future.
That's really encouraging. It means we can probably create even more powerful LTSMs down the road. But what about the data side of things? What happened when they increased the size of the data set they use for pre-training?
They saw some improvements there too, but it wasn't as straightforward. When they trained Timer on bigger and bigger chunks of that UTSD dataset, its forecasting accuracy did improve, but those gains were smaller each time they added more data.
That's interesting. Why do you think that is? I mean, if more data is generally better, shouldn't we see those error rates just keep down?
That's a good point. It's probably because they hit a point of diminishing returns with the specific data sets they used for their evaluation. Remember, they were testing Timer's forecasting ability on a fixed set of benchmarks. At some point, Timer may have learned pretty much everything it could from the data that was available. So adding even more data might not have given it any significantly new insights.
It's kind of studying for a test. At some point, you've made the material, and cramming in more information isn't going to make a huge difference.
Exactly. And this highlights something really important. Data quality and relevance are just as crucial as quantity. It's not just about having tons of data, it's about having the right data.
So it's not just about throwing more data at the problem, it's about being smart and thoughtful about what data we feed these models and how we train them.
Absolutely. And when it comes to LTSMs, this means focusing not just on making those models bigger, but also on creating larger, higher quality data sets that truly capture the richness and complexity of real world time series.
So it's a balancing act. We need both powerful models and really good data infrastructure to unlock the full potential of LTSMs.
You mentioned earlier that the researchers also compared timers to other LTSMs, especially in that area of zero-shot forecasting. What did those comparisons show?
It's a fascinating landscape. The paper gives us a glimpse into the world of LTSM research, where models like Morai, Times FM, and Chronos are all competing to see who can perform the best. Okay, so it's Timer versus the Titans. How does it stack up against those other models?
Well, it's important to remember that it's not a simple winner takes all situation. Different models have their own strengths and weaknesses, and the field is changing really quickly. The researchers were more interested in understanding the bigger picture and comparing the different approaches these models use, not necessarily finding one model that's the best.
So it's more about understanding the different ways these models try to solve time series problems. What were some of the interesting things they learned from those comparisons?
One of the most striking observations is just how popular transformer architectures have become. Just like we've seen in natural language processing, transformers are becoming the go-to architecture for LTSMs. And that's probably because they're really good at handling those long-range dependencies within data sequences.
So transformers are the rising stars in time series analysis. But even within the transformer family, there's a lot of variation. We talked about how Timer uses that decoder-only approach, while other models use a more traditional encoder-decoder approach.
Exactly. And the type of architecture you choose can have a big impact on how well the model performs and what it can do. Timer's decoder-only approach, which is inspired by language models like GPT, makes it particularly good at handling situations where there's not a lot of data available, and it can adapt to new tasks more easily.
But it's not just about architecture, right? The size of the model and the amount of data it's trained on, those things matter too.
Absolutely. And what's really interesting is that there isn't always a direct link between the size of the model and how well it performs. Some models, like Morai, do incredibly well even though they're relatively small compared to other models. And in some cases, timers, even with its massive pre-training dataset, didn't do significantly better than models that were trained on much smaller datasets.
That's fascinating. It suggests that data quality and the training methods you use are just as important as the sheer size of the model or the data set.
Precisely. It's kind of like a skilled chef who can create an amazing dish with just a few simple ingredients. It's not just about having the fanciest equipment or the biggest pantry. It's about skill, technique, and a deep understand of the ingredients you're working with.
So the main takeaway here is that there's no one perfect way to build the best LTSM. It's about finding the right balance between architecture, data, and training methods.
Exactly. And all the exciting research happening right now in this field, it's all about exploring that complex relationship and seeing just how far we can push the boundaries of what LTSMs can do.
It's definitely an exciting time to be following this field. I'm eager to see what breakthroughs come next. But before we get too far ahead of ourselves, let's step back and think about the bigger picture for a moment. What are the implications of all this research on LTSMs? Where do we go from here?
That's a great question. And I think the most exciting part is that LTSMs have the potential to completely change how we understand and interact with the world around us.
Can you elaborate on that? What areas do you see LTSMs impacting the most?
Imagine LTSMs being used to analyze financial markets, predict outbreaks of diseases, optimize energy grids, personalize medical treatments, and that's just scratching the surface. The potential applications are huge, and they span so many different fields.
It's like we're giving machines a new sense of time. And that opens up all sorts of possibilities for problem solving, decision making, even for things like creativity.
It really is a paradigm shift in how we think about artificial intelligence. But with any powerful technology, we need to be careful about the ethical implications and make sure that these models are used responsibly, for the benefit of everyone.
That's a crucial point. We need to make sure that we're not just building smarter machines, but also building a smarter, fairer future for everyone.
Absolutely. And that's a conversation we need to have alongside all those amazing technological advances. We need to be thoughtful about how LTSMs might impact society, the workforce, and even our own understanding of ourselves.
Okay, so there's a lot to think about here, both in terms of all the technical possibilities and the broader societal implications. Before we move on to part three, where we'll wrap up our deep dive and leave our listeners with some final thoughts, let's quickly recap what we've discussed in this part.
We started by talking about the challenges of scalability, and we looked at how the researchers who developed Timer tackled this by looking at how the model's performance is affected by both the size of the model and the size of the data it's trained on.
Then we took a peek at all the different LTSMs out there, all those competing models, and we talked about how transformer architectures are becoming the dominant force in the field. And we discussed all the different approaches researchers are taking to improve scalability and make progress in that really exciting area of zero-shot forecasting.
And finally, we zoomed out a bit and thought about the broader implications of LTSM research, highlighting the potential for these models to change the world in many positive ways. But we also emphasized that we need to think about the ethical side of things and make sure these powerful tools are used for good.
For part three, as we finish up our deep dive and leave you with some thought-provoking questions about the future of time and AI. Welcome back. It's the final part of our deep dive into large time series models. And it's been quite a journey, exploring what timer can do and how it could totally change how we understand time itself.
It really has, from finding those complex patterns in data to predicting what's going to happen with impressive accuracy. Timer shows us just how far we've come in creating AI that can really understand time.
One thing that's really struck me throughout this whole deep dive is how similar timer is to what we've seen with large language models. It's like we're taking those same ideas of generative pre-training and adaptability and applying them to the world of time series data.
Yeah, that's a great point. We've seen this trend of moving away from those hyper-specialized AI models to systems that are more flexible and adaptable. And it's all thanks to those advancements in model architectures, like those amazing transformers and the fact that we have these massive data sets available for pre-training.
It feels like we're seeing this convergence of ideas from all these different areas of AI research. As these models become more general purpose, the lines between language, vision, and now time, they're all starting to blur.
Exactly. And that convergence is super exciting because it opens up possibilities for solving problems in ways we never even imagined before. Imagine having models that can seamlessly use information from all sorts of sources, text, images, sensor data, all combined with an understanding of how things change over time.
It's like giving AI a much broader view of the world, allowing it to think and make decisions in a way that's more similar to how humans do it.
Precisely. And as we keep developing these more sophisticated and adaptable AI models, I think it's crucial to remember the bigger picture.
Right, we can't just focus on the technology itself. We need to be mindful of how these advancements will affect society.
Absolutely. We need to be careful about the ethical implications and make sure these models are used for good to benefit all of humanity, not just a select few.
It's not just about building smarter machines, it's about building a smarter, fairer, and more sustainable world for everyone.
I completely.
Okay, so as we wrap up this deep dive, let's take a moment to go over the key things we've learned and leave our listeners with something to think about.
Sounds good.
We started by talking about all the challenges that come with analyzing time series data, and we emphasized the need for high-quality data sets and really powerful models that can handle the complexity of the real world.
Right. And then we dove into Timer, that cutting edge LTSM that really blew us away with its ability to forecast, fill in missing data, and spot anomalies. And it did all of that with incredible accuracy, even when it didn't have a lot of data to learn from.
And we saw how its architecture, that unique decoder-only transformer architecture, helps it learn from data in such an interesting way, almost like a time traveler piecing together a story. And that approach is inspired by language models, which is pretty cool.
Yep, and we talked about how this research on Timer is just one piece of this much larger movement in AI. We're seeing models become more versatile and adaptable, and they're able to tackle a much wider range of tasks than ever before.
And we can't forget that fascinating comparison of timer to other LTSMs out there. We saw how transformer architectures are becoming super popular in this field and how researchers are always trying to improve scalability and push those boundaries of zero-shot forecasting. It's such an active area of research.
It really is. And as we come to the end of this deep dive, we're left feeling both excited and maybe a little bit in awe of what time-aware AI might be capable of in the future. It's clear that models like Timer have the potential to change countless industries and really reshape our understanding of the world.
But now we have to ask ourselves, how are we going to use this incredible power? What kind of future will we create with these time-aware AI tools at our fingertips?
Those are great questions, and I think it's so important to think about those things as we continue on this amazing journey of discovery and innovation in AI.
Absolutely. Well, that brings us to the end of this deep dive into large time series models. Thanks for joining us, and we'll see you next time.